Hey everybody, my name is Paul Abernathy, and welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. On today's topic, we're going to talk about Raceway field calculations. Whether you're an electrician in the field or you're an apprentice, you're learning the trade, you need to know how many conductors I can safely put in a raceway. And so the National Electrical Code gives us some guidance on this, remembering that the NEC, or the National Electrical Code, is a minimum safety standard, and we follow it. We're going to have the most minimally safe structure that we can have. So we definitely want to follow the National Electrical Code. Okay. Now, within the National Electrical Code, we have tables that are in Chapter 9. Now, today's episode, we're going to talk about Table 1, we're going to talk about Table 4 and 5, and we're going to talk about 5A, and we're going to talk about 8. Now, each one of these tables have their own application, and don't worry, we'll cover that as we get to each one of those, but they're the ones that we're going to focus on in this episode, and that has to do with telling us what the percentage of fill of a raceway is. It's going to tell us what the approximate area is of a conductor, of a raceway, of compact conductors, and we're even going to learn what the approximate area is of individual conductors or stranded conductors that are bare. Okay, all of that's going to be covered today, and we'll cover all those little notes that people always worry about under Table 1 or that are at the beginning of Chapter 9. Okay, so we're going to talk about all those things. So let's get started. Here we are, Chapter 9, and we have a assortment of tables that we just talked about that are referenced in all these notes. Okay, so they're all applicable. First things first, Table 1. Now, Table 1 is telling us, look, if I've got a raceway and I put one conductor in it, then I can fill that raceway up with a conductor that doesn't exceed more than 53%. If I have two conductors in a raceway, then I can fill them, whatever size they may be, I can fill that raceway up to as much as 31% of that cross-sectional area of the total area of that raceway. And now when I have 3 or more or over 2, then I can fill that raceway up and I can't exceed 40% of that raceway fill. Okay? So that's what Table 1 is talking about. So these are our percentage fill that we can't exceed, 40, 31, and 53. All right, now what about these little notes? Okay, note number 1 says, look, if I'm installing conductors in a raceway and I'm using all the same size conductors, then I'm worried about not exceeding the 40%, then I can go to Informative Annex C, and that'll tell me the maximum number of conductors or fixture wires that I can install inside that raceway. So I'll give you an example. So if I have a EMT, electrometallic tubing, and I have trade size 1, I want to know how many THHNs I can put in there. Well, I could go to Informative Annex C because they're all the same size. Okay, they're 14 gauge. If I go there, it'll say that I can put 35 in there. Okay, well, if I put 35 in there, whether I did the calculation as we're going to do later, or I simply went to Informative Annex C because the Note 1 tells me I can, then what you find out is that it says I can put 35 in there and I'm not, and that's not going to exceed the 40%. Well, that sounds great. And for an exam, no problem. If you get a question like that on an exam, you know how to answer that one quickly. It's all the same size. You just go right to Informative Annex C. That's perfectly fine. Here's the problem. In the real world, when you have more than 3 current carrying conductors, and that's given to us, if you're using ampacity, for example, and we're looking at 310.15b16 of the National Electrical Code, that's our ampacity table, and I've got more than 3 current carrying conductors, or the ambient temperature is other than 30 degrees C or 86 degrees Fahrenheit, then I have to go to some other tables because I have to do something called correction and adjustments, okay, depending on the ambient temperature or the number of current carrying conductors in there. Well, if the code says in a raceway field that I can put up to 35 in there and not exceed the 40%, if those conductors are current carrying, we got a problem because now those conductors which you thought had an ampacity based on 310.15b16, now since you're over 3 current carrying conductors, the chances are when you get up to 35, you're going to have a conductor that's hardly got any current carrying ability on it because of the mutual heating that's involved. And again, this is assuming all raceways that are over 24 inches. They're not nipples, okay? These are raceways in complete systems, all right? From box to box, from closure to closure, those type of things. So it's really important to understand that even though we're trying to solve how many wires we can put in a raceway, okay? At the end of the day, there's still things you have to consider about the ampacity of that conductor as the consequence to putting all those conductors in a raceway. Okay. Now, if you don't know how to do that, then you need to listen or watch our video, Derating Demystified. Now, that's available on our website as well as available on our YouTube channel. That kind of goes over all the deratings and adjustments and corrections and things like that, dealing with ambient or the adjustment for the number of current carrying conductors. That's a real important thing. So just because I can put this many conductors in a raceway doesn't mean that I'm going to get the usability out of those conductors at their ampacity value. It's important that we do draw a distinction between those two things, okay? All right. With that said, if they're all the same conductor size, then you can go to Informative Annex C, and that'll tell you how many you can put in. So if that's all the question is on an exam, how many 14s can I put in a trade size 1? Then the answer is 35. Okay, EMT, that is. Okay? All right, the next one we'll look at is note number 2. And note number 2 says, Table 1 applies only to complete conduit and tubing systems and is not intended to apply to sections of conduit or tubing used to protect exposed wiring from physical damage. Okay, so all of these fills right here, this right here only applies to complete systems in tubing and conduit. Okay, and so at the end of the day, we do know that 300.18 of the National Electrical Code talks about complete runs. That's from box to box. You're supposed to complete your raceway installation before you pull conductors in it. I know we all do that in those trenches out there, right? We don't put pieces together and pull the wire. We complete it and then we pull it, don't we? I bet we do. So at the end of the day, that's what that note number 2 is saying is, look, if it is just pieces for physical protection, small sections, that it's not a complete system between box to box, then I don't have to worry about the fill requirements. Okay, that's what it's saying in note 2. Note number 3, it's just reminding you that equipment grounding or bonding conductors take up space in a raceway. And because they take up space in a raceway, you're going to count them. Okay, so if they're insulated, you simply follow the same practice we're going to show in a minute, where you actually determine what the conductor is, an XHHW, THHN, whatever it is, and you go to Chapter 9, Table 5, and you'll find that conductor, and you'll have that square inch value under the approximate area, and you apply it. If it's a bare equipment ground or a bare equipment bonding conductor, then you're going to go to Chapter 9, Table 8, because that's going to give the approximate area of those stranded or solid conductors under that table. Okay, and that's where you get that information. All right. But you definitely have to account for them. They do take up space, so you have to account for that. The next one is note number 4. And this is when we're dealing with those nipples. This is conduit or tubing, and it has a maximum length not exceeding 24 inches. Okay. And it also requires that this is installed between boxes, cabinets, and similar enclosures. Okay. So that's what the nipple is. So this allows me to fill it all the way up to 60%. So up until this point, we were talking 53, 31, 40. But now, since it's a nipple, it's not over 24 inches. Okay, so it's not a lot of heat buildup here. It's open on each end. We're going to use the open area that's inside of the enclosures to help draw out that heat. And so not a concern here. I can fill it up all the way up to 60%. There is also something unique here as well that you might want to be aware of if you're taking the exam, and that is this little piece right here. It also reminds you, since you are dealing with a nipple, that you don't have to apply the adjustment factors that are found in 310.15b3a. And again, that's for the number of current carrying conductors that are in the actual raceway. So because it's a nipple, because it's short, means I get to, I don't have to apply these adjustment factors. Now, I am going to tell you that only applies to the adjustment factor. In the real world, if I'm installing it, let's say in Arizona, and it's outside or whatever, that nipple, yeah, it might be only 18 inches, 19 inches, 20 inches. And I can fill it up to 60%. If the ambient temperature up there is higher than 30 degrees Celsius or 86 degrees Fahrenheit, then I'm going to have to apply what? I'm going to have to apply an ambient correction to that. Don't forget that. Just because I'm not applying for the current carrying conductors doesn't mean that it might be a condition where I have elevated ambient temperatures that I have to take into account. Again, heat is not a good thing for conductors when it's trying to increase ampacity or current flow. Okay, it's detrimental. Okay, so that's something you want to remember. Next thing is note number 4. For conductors not included in Chapter 9, and it says such as, remember the term such as isn't all-inclusive, it's just giving you some examples. But it says for conductors not included in Chapter 9, such as multi-conductor cables and optical fiber cables, it says use the actual dimensions of that product. Okay, so where are you going to get that? That's going to be from the manufacturer. Another good example of this might be where we offer, let's say, a quad rated conductor. All right, what's a quad rate? Okay, let me explain something to you. If I'm dealing with a product that is, say, PV, USC-2, RHH, and RHW-2, that's 4 ratings on one wire. Okay, now, USC-2 is found in Chapter 9, Table 5. Okay, but PV wire is not found in it. So, PV wire is going to have a thicker insulation than USC-2. Okay, so if I'm going to put PV wire, which is all these ratings, if I'm going to put it in a Raceway, then I have to size it for the Raceway fill. Where do I get those values since it's not covered in the National Electrical Code? I get it from the manufacturer. And the manufacturer provides you with that approximate area to use in your calculation. That's what manufacturers are there for, to give you that kind of information. A real quick explanation of quad rated is many people are very familiar with that plain USC-2 underground service entrance conductors, which is also slangily used as a cable, can be bundled together or twisted together with other conductors and they're put into the ground, okay, under UL 854. Okay, direct burial rated. Gotcha, as long as it has that on the wire. However, that can't come into a building. So maybe that's outside, and then the moment it transitions into a building, like goes into a Raceway, it can magically become RHH, RHW-2. So if it does have a USC-2 with multiple ratings on it, then you can rest assured that it's probably got flame retardant properties to it, so it can come into a building inside of a Raceway. Okay, so why would we quad rate it? Well, it can be used as PV, it can be used as USC-2, it can be used as RHH or RHW-2. That way it doesn't sit on a shelf. It can be used as multiple things. It also can transition again from direct burial into a Raceway where usually plain old USC-2 can't come into a building because usually it doesn't have flame retardant on it. Now, again, remember that even if I have all those ratings, if I'm going to do a Raceway fill, I have to go to the worst case scenario, and that is going to be the PV's insulation thickness. That value is going to be greater. So I might have a triple rated product like USC-2, RHH, RHW-2, and then I might have a quad, which is PV, USC-2, RHH, and RHW-2. The one that has the PV marking on it as well, that is going to be thicker insulation, and you won't get that from the tables within the NEC. You need to contact the manufacturer. Kind of why that note is there, and we will provide you that information. Don't worry about it. All you got to do is ask for it. All right, so the next one we're going to look at is Note 6. It says, for combinations of conductors, that means they're not all the same like we had before, and they have different sizes. It says use the actual dimensions of the conductors, which you could also get from the manufacturers if they're other than what's put in Table 5. If the manufacturers do have something that differ, they're permitted to do that, but they'll give you that information, kind of like what happened with the PV up here. But in lieu of that, you have this or, which says that you are perfectly fine in using the Table 5 values, or if you're dealing with a compact copper or compact aluminum, then you can use the values that are in Table 5A. So those are the difference in the two tables, all right, to do your Raceway fill calculation, okay? Now, a couple things to remember. The Table 5A is very similar to Table 5. Now, Table 5 gives you the RHH, XHHW, THHN, all those. 5A really is, again, focused on certain types of conductors, XHHW, THHN, RHH, but it's all based on a compact conductor. Again, a difference. You have what's called concentric, which has a lot of voids in it. That's interstices. You have compressed, which is part of the die process where it compresses it down. You still have some interstices. Now, the interstices are those little grooves or little V between conductors, okay, between the strands, if you will. And then you have what's called compact. Now, compact is still stranded. It's just compacted so tightly and compressed through a die process that what happens is you have no voids in it. So it kind of looks like a solid conductor, but it is still flexible, okay? And because it is stranded, okay? So there's a benefit to using compact products in some cases. It results in smaller raceways, to be honest with you. But again, you remember when you're doing it or you're on an exam, be careful. If they ask for compact conductors, make sure you're not in table 5. Make sure you're in table 5A. Okay, I can see where somebody might make a mistake on that. Okay. All right, next one we're going to look at is note number 7, and I got a little graphic for this because this is telling you the number of conductors that I can put in a specific trade size raceway, and if I get to a 0.8 in my calculation, then I can round it up to the next whole size. So it says when calculating the maximum number of conductors or cables permitted in a conduit or tubing, it says all of the same size, okay, then I can use the next higher whole number shall be used to determine the maximum number of conductors permitted when the calculation results in a decimal greater than or equal to 0.8. What in the world are we talking about? Well, don't worry. I got a graphic. I'm going to show you. So let's go down to the graphic. So here's the example for note 7. It said, what if I had how many 14 TWs can I put in a 1/2 inch or a 1/2 trade size rigid metal conduit? Now, for 3 or more conductors, we know that table 1 says we're going to not fill it more than 40%. Okay, so it permits up to 40% of that fill. Now, if we go to table 4, that's where we're going to go, and we're going to find out what the actual internal cross-sectional area is of that trade side 1/2 rigid metal conduit. In this case, it's 0.125. Now, we can verify that by going to the code, and we'll just go and verify that. So we're going to go down to rigid, and let's see here. Oh, I went too far. Might have to scroll down for me to find it here. And once I get to it, what we're doing here's rigid, and we're going to go down, and here's the 1/2 trade size. You kind of notice it's not really inches, even though it kind of does correlate. It's still really called trade size rather than 1/2 inch. But anyway, we don't really worry too much about that jargon. So it's a 1/2 trade size. You see that it is the 40% fill, and the total area of it is 0.314. That's the total area. But 40% of that area is 0.125. So we go back, and that's what we had on our example. Okay, so it's 0.125. Now, since we're dealing with 14 gauge TW, we go to table 5. In the cross-sectional area of a 14 AWG type TW conductor is 0.0139. Okay, so 0.0139. So now let's go on and go back to the code, and let's validate that. So now we're going to jump down, and we're going to find that. So here we are for conductors. So we're going to go to TW. And we said that it was a 14 gauge, right? So here's 14 gauge right here. And we said it was 0.0139. So we're going to go back to our presentation, and we see that that's accurate, 0.0139. Now, since we know this is the total interior area, and we know what the individual 14 conductor is, then we just simply do some math here. So we use the 0.125, which is the cross-sectional area of a 1/2 trade size rigid metal conduit, and we divide that by 0.0139. Basically, it's saying how many of these can we stuff in here, and the result is 8.9. Well, since it results in a 0.8 or greater, we can round this up and say we can put 9 conductors inside of that 1/2 trade size without a problem. Okay, so that's how note 7 works. It allows us to determine how many we can put in there. And if it's 0.8 or greater, then we can go up to to the next size whole number. Okay, so 0.9 can go up to 9. All right, so that wasn't too complicated. All right, so let's go back to the code, and I'll go on and jump and get us back to where we were at. So that's what we're talking about for note 7. And you also note the little caveat here, in order to apply this one, all the same size. Okay, that was something that you have to remember when applying this rule here. All right, next one is note 8. Now, note 8 says where bare conductors are permitted by other sections of the code, probably most notably in Article 250, there's various sections there that we have no problem with putting bare conductors inside of raceways. How do you determine what the actual area is of the bare conductor? And I think I told you earlier, you simply go to table 8 and you'll see that. So now if I were to do that real quick for you and just go to table 8, you'll see that right here are your conductor sizes on the left, and here's your conductors, and here's the area. Remember, we're staying focused on area, not diameter, area. And then you'll see here, again, a familiar face, and this is the square inches. And whatever your conductor may be, if it's a 6 gauge, 7 conductor, or 7 strand, then you'll see that the area of that is right here, 0.027. Okay, and you simply would apply that to your calculation. All right. All right, so now let's go back to the notes and go to note 9. Now, note 9 is not as complicated as people make this one out to be, but we'll show you what it is. So here's note 9, and it says a multi-conductor cable, that would be like a tray cable, NMB, MC cable, optical fiber cable, or flexible cord of 2 or more conductors shall be treated as a single conductor for calculating percentage conduit or tubing fill areas. What does that mean? Well, that means if I take a MC cable, or I take a NMB, non-metallic sheath cable, that I can put that in a Raceway. Various articles for those wiring methods do permit it, and I put it in there. Then I treat it as a single conductor, and I take that cable and treat it as a single conductor. As a result, the Raceway fill is 53%. So I can't exceed 53%, so I treat that cable as if it's a single conductor. And that's how we apply it. All right? Now, let's move on with that a little bit. And it says, well, what happens if we get a cable that has an elliptical cross-section? It says the cross-sectional area calculation shall be based on using the major diameter of the ellipse as the circle diameter. What in the world does that mean? So let's kind of go to a graphic, and I'll kind of give you an illustration. So here's what we're talking about. So in this graphic, you see the Raceway, and we'll assume it's a complete Raceway that we've got this NMB running into. We just cut it in half here so you could see it. Again, it's all about being a complete run, okay, a complete between box to box and closure to closure. If it was just sleeve through it for physical protection, then the fill wouldn't be any issue anyway, right? Okay, just so we're on the same page. So where do we get this major diameter? You get it from the manufacturer, okay? Now, you could measure it and do that as well, but usually the manufacturer will provide it on a cut sheet. Now, once you do that, there's a formula that you can use, and here's the formula right here. And it is pi divided by 4 times the diameter squared, okay? So we translate that. Pi is 3.14, but we just take it all the way out to the 4 digits. So it's 3.1415 divided by 4 times 0.450 squared. Now, notice that we get the diameter here is 0.450 inches. So that's the value here, and that represents the diameter, and that's the major diameter. So let's do the math even further. So always do the first part of the equation, or do what's in parentheses first. We learned that from our algebra. So it's 3.1415 divided by 4 equals 0.785375 times, and we took the 0.450 squared, that resulted in a 0.2025. So then we take this value and we multiply it by this value, we get 0.1590 square inches. That is our new area. So we're treating this as if it is a round conductor, and we use the major diameter to achieve that. So how would we find out what Raceway we could put this in? The same way we did before. We simply go to Chapter 9, Table 4, determine what Raceway we're working with, and we make sure that we find a Raceway that is not more than 0.1590, or actually can handle 0.1590, but we don't want to exceed 53%. Okay, so in our case here, let's say, what size EMT could we put this in? Well, it's 0.1590. All right, let's go to the code real quick, and we'll look at it. So here's the code, and we're going to go down, and we're going to say we want to put it in EMT, and we need to see it. So here, we know that our value, and again, just so we'll all see it, it is 0.1590. Okay. So I go down here, 0.1590. Well, I can't be in 0.12, but here it says 0.213. So I was in 0.15. So obviously 0.213 is okay. So it would be a 3/4 trade size is what we would do. The 0.122 is too small. We needed at least 0.15, okay? So That's how you would size it. So for this application right here, I would expect for this to be a 3/4 EMT in order to be able to put this size conductor in there, all right, or this size cable, all right? Actually, take that back. Did you see what I did? Did you see how quickly this can happen to you on an exam? How many of you caught that out there? Well, I kind of was a setup, but I wanted to see what you thought about it, and you didn't say anything because obviously this is a recording and you can't. Why am I not using this? Why am I using this column? Let's jump over here. Remember what I said about the cable? It can be used as, it has to be considered one wire. So I can fill it to 53%. So now what changed? Well, is 3/4 wrong? Well, not in the real world if I want to put it in there. And if you've ever pulled any NM in some raceways, and you're going to appreciate a bigger raceway. But in reality, check this out. The half trade size is 0.161. So that is actually, on an exam, the accurate answer, because 0.161 is greater than our example, which was 0.1590. Okay? Now, the point being in that example was to make you think. Immediately, we're so used to do the 40% that we said, we'll go right to the 40%. Yeah, in the real world, it wouldn't be wrong. I mean, to be honest with you, I could pull an N and B in a trade size 4 if I wanted. I don't know why, but I could. On an exam, you want the best possible answer. And in this case, since it was a cable, and because Note 9 says you treat it as a single conductor, that's what put me in the 53%. See how easy that can happen? Just keep that in mind when you're taking an exam. Slow down, take your time, but that's how quickly it can happen. All right? That was a good example. All right, so now let's go back up here and finish out Note 9. And the Note 9 goes on to say that assemblies of single insulated conductors without any overall covering shall not be considered a cable when determining conduit tubing or tubing fill area. What does that mean? Well, that's significant because there are many people that get in a bind out in the field. Let me give you a great scenario. They put their raceway in. They pulled the conductors, or they sized the raceway wrong. They didn't know how to do raceway fill. And they did the conductors. They got something wrong, and now the raceway is too small. They've got 48% of conductor cross-sectional area. And they're like, oh my God, now it's over 2. I can only fill up to 40% of that raceway, and I've got 48% of cross-sectional area of conductor. I can't use it. What do? Well, they plex it. They think they twist it together, and now they treat it as a cable, and they say they can go up to 53, and then they put it in, and they circumvent that 40 limitation, and they go up to 53. I'm here to tell you that you can't do that. You in the field cannot twist. You could twist them, plex them if you want. Sometimes it pulls easier that way, but you cannot make a cable in the field. Okay, manufacturers make cables. Just because you twist individual conductors together doesn't mean that I can utilize that 53% advantage, okay, that you get with a cable. All right. In this case, they're trying to be an advantage. It's still going to be a 40%. Though if there's 4 conductors and you plex them or twist them together, it doesn't matter. It's not a cable. You can't use 53%. It's still 40%. Okay. Keep that in mind. That is reserved for things like NMB, for tray cable, for MC cable, AC cable, all those type of things that you can pull in raceways. There's no problem with that. But you can't exceed the 53%. Just taking individual conductors and twisting them, that doesn't make it a cable. Okay? Just keep that in mind. All right, and then lastly, let's go on down to number 10, which is the easiest one of them all. All this is saying is the values or approximate conductor diameters are shown in Table 5 are based on worst case scenarios. That's a good thing. I always like that worst case scenario. Okay, and the only other thing that I will say of any significance, because you know you're just going to use Table 5 for all exam purposes for a raceway fill, unless it's compact, round, and if it's copper or aluminum, then you're going to use Table 5A. Just remember that. And the last line here is critical because all of us manufacturers vary our productions. So it says, if the actual value of the conductor's diameters and area are known, then they shall be permitted to be used. So again, long story short, most of us are going to just tell you to use the values that are in Chapter 9, Table 5. but for some reason we produce a product that has maybe a smaller area or something, still got to meet the circular mills for that conductor required size. But let's say whatever we do, let's just say we have values that show it differently, then the manufacturer could provide those. And if they're known, you can use them. Okay. But most of the time, people are going to use Chapter 9, Table 5 for all the conductors that are known. PV, for example, as we talked about earlier, you're going to get those values from the manufacturer because that's not something that's in the NEC. Okay. All right. So that pretty much covers all the notes. Okay. So now let's kind of look at this table here. So this is what Table 4 looks like. Okay. Now it gives you the percentage fills for over 2. We saw earlier the 40%. It has the 60% for the nipple. It has for the one wire, it's 53%, and our cable in our example a minute ago. Okay, 53%. Here's your 2 wires that can't exceed 31% of this total area over here. So these are percentages of this total area. Now, a couple things to remember. If you ever get on an exam gives you all these values, okay, all these conductors and everything. And the end of the question, all it said was, give me the total area of a 2-inch EMT. If that's your question, all of those values on the conductors mean nothing because all they're asking you for is the total area. And if that's the case, then this is the total area. So while they might give you all the conductors to worry about, at the end of the day, they ask you what the total area was, a 2.5 trade size EMT, then it literally, and again, make sure you have a straight rule so you don't mess up as you go across. The total area is 5.858. That's the total area, okay, in square inches. And that was just as simple on the question, okay? Another thing to remember is in your calculation, they might do everything in millimeter squares. I kind of doubt it, but if they do, if they give you a question and they want it in millimeter squares, make sure you don't make the mistake and do half of it in millimeter square and then turn around and start using square inches, okay? Don't get them confused. If they give you the question in millimeter squares, stay in it, okay? I don't think they will, but if they do, stay in it. Most of the time, that's going to be in square inches, okay? All right. Just kind of a little tip in case you run into that. All right, so now we have this table for EMT, ENT, that's our electrical non-metallic tubing, FMC, flexible metal conduit, all of them here. And this is where you're going to go to find out what your 40, your 60, your 53, or 31. Okay, so we already done it for you, so that's a beautiful thing. Now, let's look at Table 5. Now, Table 5, you want to make sure that you're firmly in the approximate area. And again, we're working firmly in the square inches. And down here is the approximate area in those square inches of all of the different type of conductor insulation types. Okay, RHH, RHW, RHW-2, all of them TW like we were looking at earlier. You've got the THHN, THWN, you've got XHHW, all of these values that are all here. Now, the one I want to caution you about, if you get an exam question and they ask you something about without outer covering, and it's RHH, RHW, or RHW-2, bear in mind that both RHH and an RHH without covering exist in this chart. See the asterisks here? These approximate areas are going to be different, okay? So keep that in mind. So there is also, like I'll show you up here, there is some RHH, RHW, RHW-2 that does have a covering, and you have to be aware of that. Don't get fooled. Watch the question on the exam, because if it asks you for the area and it uses RHH without a covering, that you know that you need to look for the one with the asterisks. Okay, so if I was telling you to highlight anything on an exam in this table at all, then I would probably tell you to do this. Highlight this down here, okay? That's probably what I would tell you to highlight, all that down here, okay? All right, so with all that said, let's go on and move into our example, all right? So let's go to the PowerPoint, and I'm going to come down. All right, so here we go. We have an EMT tubing. Really, it's going to be this simple. I've got 350, 350, 350. I got a 250, and I've got a 3, okay? So XHHW-2 is what we're using. So I've got it. So let's start putting the things together. We don't really know. All we know is it's an EMT first. Now we have to see what the total cross-sectional area is of all these conductors combined. So I've got 3 350s. So what I'm going to do is I'm going to go to the code. and I'm going to go to XHHW right here, and I'm going to go to the 350, and you see that it should be 0.5166. So I'm going to go back to my graphic, and you see that it was 0.5166, and there's 3 of them. So I do that times 3. So for those 3 350s, it's 1.5498 square inches. Okay, that is the approximate area for those. All right, so the next, oops, cheating on you. The next one is 250. All right, so we go back to the code, and we're going to look for the 250. Here it is, 0.3904. Again, you're under approximate area, and you're in the square inches, and you're making sure you line up the type of insulation you're dealing with. Okay, all right, so there we go. So it's 0.3904. All right, so let's go back to our graphic. And you'll see that is 0.3904, and there's only one of them, so we'd add that value over here. Okay, we're just simply adding them up. So the next one is a 3 AWG, American Wire Gauge, XHHW-2. All right, so now we're going to go back to the NEC, and now we're going to go find that 3. There's the 3. Come over here. Again, we're dealing in approximate area. Stay away from the diameter. Stay with the area. Come down, and you see it's 0.0962. Okay. All right. So that's what we should see on our graphic. And there it is, 0.0962. Now you'll notice this says HXXW. That's an error. It's supposed to be XHHW. I got dyslexic on that one line. Sorry about that. But anyway, that's what it is. There is no such thing as HXXW, by the way. Okay. All right. So it's 0.0962. Now what I got to do is add these up. So the 1.5498 plus 0.3904 plus 0.0962 results in a 2.0364 square inch approximate area of all these conductors. Now, I need to go to the ENT tubing in Chapter 9, Table 4, and see what raceway is going to hold all these conductors and not exceed the 40% fill requirement. All right, so let's go back to the code. All right, so we're going to zoom up here and go back up, and we know where EMT is right here. And we're in the over 2 wires. Make sure you check yourself. Remember how we did that with the single cable that was used as a single wire? Here, we're over 2, so we're good here. Now, we had to worry about 2.0364. So we come down here, and we have to find a raceway that can accommodate that and not exceed the values of the 40%. Well, what about this 2? Well, that's 1.342. That's not enough to house our 2.0364, because if we did try to put it in there, we'd be exceeding the 40%, because this is the 40% for that size. The next one is 2.5, and that is 2.343. Well, can we put 2.0364 of cross-sectional area of conductors inside a raceway that is overall, it's 5.858, but 40% of it is 2.343, so we're obviously not going to exceed the 40%. So our raceway, for our example, is going to be trade size 2.5. Now, let's talk about a couple things that you might see on an exam around this concept. See this area that's available in here? Well, we're only dealing with 2.0364. But the total area in here that's not exceeding 40%, okay, not the total overall area, but the remainder that we could add to it that doesn't exceed the 40, we can calculate for that. So let's go back to the code. So if you get a question like that, it's as simple as saying this. This was the 40% fill. My conductors only took up 2.0364. So take this value here, subtract 2.0364 from this value, and the result is 0.3066. Okay, well, in that case, I could install additional conductors inside this raceway, up to 0.3066 worth of conductors. Okay, so I could put just one bigger conductor in there, as long as it doesn't exceed 0.3066, or I could put a couple smaller conductors in there as long as I don't exceed that 40%. And so I have an additional 0.3066 to play with. Okay. Now, also on an exam, and that might be what they ask you. They say, what is the remaining? What's the remaining area up to the 40%. Okay, however they word the question, and you're looking for that little area that's remaining. Another question they might give you is they might tell you how many existing conductors are in a raceway, and now they want to know how many additional 14 conductors can you add. Well, you do the same thing. You take the 40% because you know you can't exceed the 40, subtract the value of the conductors that are existing, and whatever that value is remaining, then you take that value divided by the 14 gauge conductor size that we saw in the Chapter 9, Table 5, and that's going to tell you how many additional ones you can put in there. Okay. Now, since they're different, maybe different sizes in there, remember you can't use Note 7, but that's how you're going to find the remaining area of that raceway that still doesn't exceed the 40%. Now, the same thing would be done for the 60. Okay, the same thing will be done that way. So don't get the two confused. It's just that simple. And that's how we would actually do the calculation. Okay. Well, that pretty much covers most of that type of stuff. I guess the only additional thing that I want to talk about is to kind of, you see this with Table 4. I want to give you a quick look at the Table 5A again. And again, you see here, it's dealing with all these conductors, THHN, XHHW, THW, THHW, USC, all that. Then here is the approximate area. So usually I tell students to highlight approximate areas because that's generally what you're working with. So I highlight approximate areas. I might highlight that approximate area. Okay, I might highlight that approximate area. And I go on down the line because that's what I want to make sure that I stay in the approximate area. And then I also would do this because I'm drawing my attention to it. So I might highlight these as well, okay, the square inch values. I want to make sure I don't make a mistake. So again, this table right here differs from Table 5 because this is dealing with compact copper and aluminum, okay? So I just probably highlight that if I was taking an exam just to kind of trigger that for me, all right? So that's telling you. Again, also remember you have this little thing about without outer covering as well. So mainly keep that in mind if that's what applies, okay? All right. Last one I'd probably show is going to be, again, Table 8. That's where you're going to get the bare conductors area. And again, it's in square inches down here, okay? That's what you're going to do. All right. Well, that's pretty much all I'm going to show for this video. I really just wanted to show you that it's that simple to do your Raceway field calc. If you have any questions on any of this, please feel free to email me at info, that's INFO. I should probably put that on the screen somewhere in the future, or maybe down in the ticker. But it's info at Master the NEC. That's what you got scrolling across right there, masterthenec.com. So if you want to email me, just go info at masterthenec.com or info at electricalcodeacademy.com, and I'm more than happy to answer any of your questions. I hope you got something out of this. Raceway field calculations aren't tough. You just need to slow down. Remember, there's certain things that they can trip you up on. Again, probably one of the most easiest ones to trip you up on is dealing with compact conductors, and you go to Table 5 when you really should have been in 5A. Always solve for the best possible answer. On exams, always remember copper unless they express otherwise in the exam instructions. But again, it's really simple to do. Again, if you have any questions, email us. Visit our Facebook page. We have 2 groups on Facebook. If you're preparing for an exam, go to our closed group, which is search for Master the NEC, 3 separate words, and you'll see that it's closed group. We'll ask to join. If you get a question that says, are you preparing for an exam, and you answer yes, then I'll let you in. If you're just there because you're already experienced and you just want to join, then I won't let you in. If this is exam prep, this is for people who need to pass an exam. That's the kind of topics in there. Trust me, if you're a master electrician with 40 years of experience, you're going to get bored in there because we're trying to help people pass exams, all right? Now, if you want to post questions that are like people that have a lot of experience, then use the public forum. So we have a Master the NEC public forum and we have a private forum. Okay. Visit our website, watch our videos on the YouTube channel, listen to our podcast, all available from our website, also available on Spreaker, iHeartRadio, Spotify, TuneIn, all those outlets, Spotify. You can listen to all of our shows. So hopefully you got something out of it. Until next time, stay safe and God bless.